Every year, over 440 nuclear reactors worldwide quietly power cities, industries, and lives, generating nearly 10% of the planet's electricity. At the core of this clean, high-output energy, a small, unassuming object, the uranium fuel pellet. Just one can power an entire home for a year, but behind this dense little cylinder lies an extraordinary industrial ballet, one of extreme precision, automation, and science. And at the heart of it, machines spinning at a mind-blowing 70,000 revolutions per minute. This is no ordinary production line. This is the world of uranium fuel fabrication, where raw mined rock is transformed into one of the most powerful energy sources known to man. It all begins underground. Uranium is mined from deep within the Earth's crust, usually as uranium ore, a dense, rock-like material containing the naturally radioactive element uranium-238, and in much smaller quantities, uranium-235, the isotope needed for fission. Mining operations vary from traditional open-pit and underground methods to in-situ leaching, where chemical solutions draw uranium directly from porous rock formations. Once extracted, the raw ore is crushed and treated to extract uranium oxide concentrate, also known as yellowcake. It's a fine, mustard yellow powder that marks uranium's first step toward fuel. But yellowcake is still chemically unstable and it doesn't burn in a reactor. First, it must be converted, enriched, and fabricated. The next stop is a conversion facility. Here, yellowcake undergoes chemical reactions to become uranium hexafluoride gas, UF6, the only form of uranium suitable for enrichment. It's here that temperature and pressure must be precisely controlled, as UF6 sublimes easily and must remain stable during handling. The resulting gas is stored in sealed cylinders and transported under strict regulatory oversight to enrichment plants. Now comes the phase where 70,000 RPM machines take the spotlight. Natural uranium contains just 0.7% U-235, far too low to sustain a stable chain reaction. Most nuclear reactors require enrichment levels of 3% to 5% U-235. To achieve this, UF6 is fed into gas centrifuges, tall cylindrical machines that spin at speeds of up to 70,000 revolutions per minute. Inside each centrifuge, the principle is deceptively simple: centrifugal force. Lighter U-235 molecules move toward the center. Heavier U-238 atoms move outward. But in practice, the engineering is staggering. Each centrifuge must maintain precise rotor balance within microns and spin in a vacuum to avoid air friction. These machines are clustered into massive arrays called cascade halls, where thousands work in series to gradually enrich uranium across multiple stages. The enriched UF6 is then cooled and converted back into a solid, this time as uranium dioxide UO2 powder. This powder is jet black, incredibly fine and stable under ambient conditions. But the journey is far from over. The powder is transported to fuel fabrication plants, clean, sealed facilities often operating under intense security and air control. Every gram is accounted for, every movement logged. Here, uranium dioxide is pressed into small, dense cylinders called fuel pellets. Each pellet measures just about 1 centimeter tall and 1 centimeter wide, but packs the energy equivalent of nearly 1 ton of coal. To make these pellets, the UO2 powder is compressed using hydraulic presses at pressures exceeding 10,000 psi. The resulting green pellets are still fragile like chalk, so they're baked at temperatures of around 1,700 degrees Celsius, 3,092 degrees Fahrenheit, in a hydrogen atmosphere kiln, a sintering process that fuses the particles and gives the pellets their final hardness, density, and dark, glassy finish. Pellet quality is non-negotiable. Each batch undergoes rigorous dimensional inspection, density testing, and ultrasonic scanning. Some facilities use automated laser micrometers to measure each pellet's height to within 0.01 millimeters. The approved pellets are now ready for assembly. They're inserted one by one into zirconium alloy tubes, a material chosen for its strength and low neutron absorption. These tubes, called fuel rods, are sealed at both ends with precision welding. Depending on the reactor type, dozens or hundreds of rods are arranged into a fuel assembly, a rectangular or cylindrical bundle engineered to exact specifications. Each fuel assembly is a feat of mechanical and nuclear engineering. It must withstand years of high-temperature, high-radiation operation inside a reactor core. Tolerances are tight. The alignment must be perfect. Even minor deviations can trigger rework or rejection. Throughout the entire process, automation plays a crucial role. High-speed robotics handle repetitive tasks like pellet loading and rod insertion. Sensors track position, mass, and radiation levels in real time. But human expertise remains vital. Engineers monitor air purity, control software logic, and safety compliance. Quality assurance teams conduct random sampling and live validation, ensuring that every assembly meets reactor-grade standards. The finished fuel assemblies are carefully cleaned, inspected, and placed in shielded transport casks. Each cask is built to survive a 30-foot drop, a 30-minute fire, and complete submersion. Standard tests enforced by international nuclear transport protocols. Once loaded, these fuel casks begin their journey to nuclear power plants around the globe. Whether it's a light water reactor in France, a boiling water reactor in Japan, or a small modular reactor under development in the US, these fuel assemblies are ready to power the world for up to 6 years at a time before being retired as spent fuel. Behind the scenes, innovation continues. Researchers are experimenting with accident-tolerant fuels capable of withstanding higher temperatures for longer. Others are testing thorium-based fuels, uranium nitride pellets, or 3D printed fuel geometries designed to enhance cooling and reduce waste. Global consumption is on the rise again. With the push for carbon-neutral energy, more countries are turning to nuclear as a reliable low-emission baseload solution. That's fueling a new wave of enrichment contracts, modernization of legacy plants, and even small mobile reactor designs for remote areas and military use. And yet, amid all this scale, speed, and complexity, there's a quiet continuity. The fuel that powers a city still begins as ancient rock pulled from the earth. The technology may be cutting edge, but the mission remains timeless. Safe, clean, reliable power. From crushing stone to spinning gas at 70,000 RPM, from high-pressure presses to the glow of reactor cores, the journey of uranium fuel is one of precision, perseverance, and potential. So the next time you flip on a light, charge your phone, or stream a movie, consider what's behind that power. The science, the engineering, the 70,000 RPM machines working invisibly in the background to keep our world running. If this deep dive sparked your curiosity, there's more where that came from. Give this video a like if you learned something new, subscribe to the channel for more behind-the-scenes stories of how the world really works, and drop a comment to tell us what process you want us to explore next. Thanks for watching. Stay curious, stay energized.